This talk is called The Post-Hawking Universe, with a nice subtitle. And it's a great title. I can take absolutely no credit for it. Joe Thackwell made the title, and I approved it. But this is, it's about things that we do know and things we don't know, and the sort of idea of wonder. So since it's about the post-Hawking universe, the natural place to start would be talking about Stephen Hawking. So Stephen Hawking is someone who I think most of you know. Very unfortunately, he passed away just about a month ago. But he was an absolutely amazing physicist, cosmologist, someone whose work, even 40 years ago, his work is still sort of resonating in the halls of physics and astronomy today. Of course, in addition to doing really interesting work about gravity and black holes, he also is well known for having a disability, ALS, which was diagnosed in his 20s, and basically made him wheelchair bound for most of his life. But despite that, he lived life to the fullest. There's an amazing number of stories about him, and basically the triumph of mind over matter, mind over body, really. I met him in 1988. Let me just say a few words about him. I didn't know him very, very well, but I was influenced by him quite a bit, as many people were. When I was an undergrad, like you guys, I decided I wanted to go work with Stephen Hawking. And so I got, as Elizabeth mentioned, a Marshall Scholarship, went to Cambridge, England, and to go study with Stephen Hawking. And I was there for 2 years. I can maybe just tell 2 anecdotes about him, one from the very beginning when I got there, one from the end. When I got there, there was a welcome reception, sort of a welcome to new students thing. I got all these new students into this room. There's some food, some drink, a little music, and we're all standing around because we don't know each other, and we're just kind of like, okay, what do we do? And in wheels Stephen Hawking, and we're like, wow, that was cool. Now really, what do we do? Because we didn't know if we could talk to him, and it was kind of weird just to talk to each other with him there. And then he just went out in the middle of the floor and started dancing, basically moving his wheelchair back and forth. And this guy who was, in a wheelchair was like the life of the party. It was just an amazing, amazing moment. At the very end of my time there, after we'd taken some exams and they decide who gets to stay on as a PhD student, I was summoned into his office. You get these, back in those days, this is like ancient history, so they didn't use email back in Cambridge. They used these little notes that you'd show up in your little pigeonhole. And I got these little things saying, Professor Hawking would like to speak to you. And so I went down there, and he was talking to some eminent physicist. He saw me, he kicked that physicist out of his office to talk to me, which made me feel great, which is what he does that, he did that. There are many stories about him doing that. And I sat down, and he basically offered me a position to be a PhD student of his. And at that point, for various reasons, I had decided I didn't want to stay in England, I wanted to come back to the US. And so I told him that, and he was very gracious, and he said he wished me luck, and he told me who I should work with in the United States. Just an amazingly large person. And this contrasted very sharply with everyone else in Cambridge, who thought that my saying no to Hawking was like the dumbest career move in my entire life, right? That would be the end of me. He didn't have that attitude at all. So I could go on and on about stories about him. You can read obituaries where you hear about him. I should say that these obituaries often make him look like not only a genius, but also a saint. He actually wasn't a saint. There are things he did which I could tell you about after the camera goes off. But nevertheless, he inspired many people, including me, and is sort of still, I think, sort of an embodiment of this sort of triumph of the human spirit. It's really an amazing story. Okay, next slide, please. So Hawking, in addition to talking about physics and cosmology, was not at all reticent about talking about the implications of his work for bigger issues, other issues, including the issues of philosophy, religion, spirituality. In The Brief History of Time, which is his big breakout book, which was published in 1988, there is, for example, an excerpt here where he says, so long as the universe had a beginning, we could suppose it had a creator. But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be. What place then for a creator? So he's talking about the implications of a particular theory he had for the beginning of the universe for people who believe in a creator, or more generally, God. And he went on after that to expound on this, explain several times why he was an atheist and why he believed there was really no reason to have religious faith. So I'd like to basically use that as a jumping off point. Here's a very respected physicist. What credence do we give to his opinions? A quick observation here. He's talking about basically negating the need for a creator or God based on the beginning of the universe. Something that I think many of you would probably, many of you at least who are Christians, would probably say is that you don't necessarily think that that is the only role of a God, right? If I were to ask those of you who are Christians, and I know there are some non-Christians in the audience, but if I were to ask Christians in the audience, how many of you believe and have faith in a God because the one reason is because you want to know how the universe began? How many would say, yes, that's the primary reason? Very few of you, right? There are other reasons people of faith have for believing in a God. Nevertheless, it's still an interesting question, I think. And so we'll basically put that aside. We can talk about it in the discussion. But put that aside and still jump off from this and ask the question, what does what we have learned about the universe, and maybe more generally physics, even more generally science, what does that have to say about religious faith? Is it compatible? Does it negate it? Does it have anything interesting to say about that? Okay, next. So to do that, what does what we have learned about the universe have to do with religious faith? We have to talk about what have we learned about the universe, right? So let me now give you a little bit of an explanation of some of the recent progress in the field of physics and cosmology, understanding the universe at large. So this is my field, and so I'm in the physics department at UCI. Physicists, if you know any of them, you probably know that they think they know more or less everything. And so our field is large. We're supposed to be able to think about lots of different things. But one way to organize it is to talk about what are the sort of sizes or length scales of the things you're studying. So there are subfields of physics. For example, if we start in the middle here with these things that are computer chips, if you can see them, that's condensed matter physics. And so that's sort of things that are about this size, right? Sort of very human things that can be in the palm of your hand. If we go down, there's atomic physics, nuclear physics, particle physics. And if we go to larger scales, there's that DNA thing is supposed to represent biophysics, the study of the physics of life, living organisms, planets, galaxies, and things like that. Okay, so one can organize thought in physics along this scale. So what I want to do is go, yeah, we can go to the next slide, is talk about the extremes, which are the ones that Hawking worked at and the ones that I also work at. So on the very large frontier, what is it that is at the frontier of knowledge when we're pushing the envelope, trying to talk about the largest things? Well, to make contact with things that you learn in elementary school, there's of course the sun, and there's planets around the sun. That's our solar system. This is actually a terrible graphic because, you know, if we were actually that close to the sun, we'd all be dead. And if you look very carefully, maybe some of you can see there's still Pluto as one of the planets on this diagram. So that dates the picture, okay? But anyway, you got the idea. The sun and the planets, that's a very large scale. But we now know that that whole thing is only one star in the galaxy. And so if you can see, there's a little arrow basically saying you are here. That's our sun in the middle of a large number of other stars in the galaxy. So that's at 10 to the 17 meters. The galaxy is actually only one of many galaxies in the universe, and so there's clusters of galaxies. So on this diagram, every point is a galaxy. And then at the very largest scales, there's the universe as a whole, and that's consisting of lots of clusters of galaxies, and it's at length scales of like 10 to the 26 meters. So truly, literally, astronomical length scales. On the next slide is the small frontier. So what are we learning on that side? Well, we have atoms, and again, making contact with the things you knew a long time ago. There's an atom with electrons circling around a nucleus. If you look into that nucleus, you find that it's actually made out of protons and neutrons. And now we're getting to very small length scales and the minus 13 centimeters. And we actually know that protons and neutrons are not fundamental particles. They're actually made up of smaller things called quarks. And these quarks have funny names, but basically you take 3 quarks to make a proton, 3 other quarks to make a neutron. And that's basically the sort of extent of our knowledge of how the basic building blocks of matter are arranged right now. So what do we now know? If I were to summarize all of knowledge at these 2 different frontiers, I would say that on the large frontier, a huge amount of effort, tons of observations and theories and interactions between theories and experiments have shown us that the universe consists of 3 things. There's atoms, that purple thing, dark matter, which is 27%, and dark energy, which is 68% of the universe. Okay? On the small frontier, we now know that there are a whole bunch of other particles. So if you look at this one here, here's the electron. So that's something we have known for over 100 years. There's an up quark there, that U, and a D for down quark. That's the little quarks that make up protons and neutrons. But there's a whole bunch of other things that we've now discovered, things like called neutrinos, gluons, W and Z particles. The very latest in this zoo of particles is that H in the middle, which stands for the Higgs boson, which was just discovered 6 years ago. But that completes what's called the standard model of particle physics. This is the standard model of cosmology. And in many ways, these are huge triumphs of human thought. These are sort of the synthesis of decades-long work. Now, what's interesting about it, though, is if you take these 2 bodies of knowledge and you try to mesh them together, it turns out that all the particles we know about, all the ones that were in the right-hand circle, the quarks and the electrons and all that sort of stuff, they all fit into this category here. They all fit into atoms. They're all in this little slice of the pie. In other words, everything that we understand, everything that we've seen, everything that makes up the chairs and the air and everything that we know about is only making up 5% of the universe. 95% of the universe is stuff that we just don't know what it is. 27% of that is dark matter, which does not shine or reflect light. It's not atoms, it's not neutrinos, it's not anything we know about. And then 68% is this thing called dark energy, which is even more mysterious. It's not even matter. Okay, this is the state-of-the-art knowledge of our universe right now, if you ask the best people in the world. Okay, so next one. So one particular piece of that puzzle is the dark matter, which you remember was like 27% of the universe. That's actually what I specialize in, trying to figure out what that stuff is. But let me just try to drive this home, the depth of our ignorance. This is a modern view of what a galaxy is. This thing in the middle is the typical stars and stuff that you see swirling around each other, okay? And that's not the only thing, though. What we now realize is the visible galaxies are only little islands in an ocean of dark matter. And that ocean of dark matter is represented by this blue stuff. Of course, it's not really blue. It's artificially colored in this, right? It's dark, it's black, it's transparent. We can't see it. But that is actually what's out there. And so we know about that little island in the middle, but what that other stuff is, we really have no clue. And we're trying to figure that out now. Okay, so let's go on to the next slide. So what do we need to know if we're trying to understand Hawking's statement? What we need to do is figure out the past of the universe. What we know now is the universe is expanding. That is, things keep moving farther and farther apart as time goes on. And so what we would do is basically take the current state of our universe. We know if we go forward in time, things move apart. But we want to go backward in time. We want to play the movie backwards. And so things get closer and closer together. And if you do that, what you find is that the universe appeared to start with a big bang. Okay? A time when the universe was very small, dense, and hot. Now, unfortunately, the fact that we do not even know the current contents of the universe, like dark matter and dark energy, makes it pretty hard to extrapolate to the past. So if you go before 1 second after the Big Bang, things get pretty hazy. We don't really know how to go beyond that. And so the actual state of affairs right now is that modern cosmology does not give a definitive answer, a scientific definitive answer, about whether the universe had a beginning or not, despite what you might read in papers and things. Now, how does that relate to, say, the biblical account of creation? I think it's very interesting to put this in a historical context. Okay? So if you go back to 2,000 years, but even 400 years, to say the 1600s, this is what was known about the universe. The universe is fixed. The stars are fixed, they don't move. And space and time are just basically coordinate systems on which you label things. So you can basically set up a grid, and you can label things by where they are with a 3-dimensional grid, and when they are by one other dimension. And basically that's it. The universe is a static object, stars don't move, everything is fixed. In the 1900s, and that's, let me say, that's pretty hard to make consistent with the creation event, right? It makes it look like the universe already existed forever. It's a static thing, it's just been there forever. If you go only 300 years down the line, 1900s, people start realizing that that's a completely wrong picture of the universe. Stars move, space-time is dynamical. That means it can curve and expand and things. So this is a picture of a better grid than that one, a more up-to-date one. And you see that there's sort of a warping of the space-time fabric there. And through the work of Einstein, we realized that actually space-time is dynamical. It has its own forces and things. And through the work of a Catholic priest, Lemaitre, we realized that there could be this thing called the Big Bang, which he called the primeval atom, and which basically was the beginning of the universe. So actually, the current state of affairs is totally remarkable if you go back far enough in history and view it. Basically, the scientific understanding of the universe and how it began has basically never before in history been as consistent as it is now with the creation event. So this is not a proof that there was a creation, but scientific proof. Proofs are very hard to come by in this sort of field, but it's a statement that the science is getting closer and closer to the sort of biblical account of creation. Now, if you, okay, so that's sort of my response to what Hawking said, okay? And now what I'd like to do is kind of circle around and get at some of the other assumptions that are in Hawking's statement. So one is the God of the gaps. So if you remember, Hawking said, I have a theory which explains the beginning of the universe, and so what role is there for a God? This is a classic God of the gaps argument. What it's saying is that here's how the world works. We have God to explain things we don't understand, like lightning, say. And so then, once somebody understands lightning is electricity, all of a sudden God's role is diminished. And then maybe we have God to explain rainbows, but then we understand rainbows are just optics. And so then God's role diminishes. Every time science makes an advance, then the role of God gets smaller and smaller. And given how amazing science is, God is now painted into a corner and stuck with very little to do. That is a common perception of how science and religion are related by everyone except for people who are actually religious scientists. I don't know of a single religious scientist who thinks that that's their relation and that's what they're doing. A much well, a nice illustration of this sort of conflict and the way it sort of works out is something I read in a physics magazine called Physics Today 4 years ago. Xian Yang, who is an extremely eminent physicist, a Nobel Prize winner, and actually as an Asian American, one of my heroes growing up, he wrote an article about James Clerk Maxwell. Maxwell, maybe some of you know, came up with Maxwell's equations, which are the equations that describe electricity and magnetism, and amazingly also light. So he's the guy who basically said, you know, that lightning, which is electricity, and that magnet that's on your refrigerator door, those are not independent things. They're actually described by the same theory. And in fact, the lights that's coming out of these light bulbs here is actually the same theory too. This synthesis of three things that he did is one of the greatest achievements in physics history, and was one of the greatest sort of aha eureka moments that anyone's ever come up with in science. And so Xian Yang was reviewing the work of Maxwell, and he noted that Maxwell was a religious person. And so Yang said, I wonder whether after this momentous discovery he had, basically that he unified all these different things, whether he had in his prayers asked for God's forgiveness for revealing one of his greatest secrets. He's basically saying, poor old Maxwell, he's religious, and yet he's doing this science work, and now he's figured out something, and the God that he believes in is now smaller because of that. And I don't know if Xian Yang was joking or not. I don't think he was. But if you actually go and ask Maxwell what he was thinking when he was doing this work, you get a very different picture. He said, I think men of science, as well as other men, need to learn from Christ. And I think Christians whose minds are scientific are bound to study science, that their view of the glory of God may be as extensive as their being is capable. So what he's basically saying in this 1800s English, I think, is that I study science not at the risk of reducing God's role in the universe, but because I am able to view the glory of God when I study science. I learn amazing things about how the world works, and because God created the world, I learn amazing things about God. It's a very different view from the God of the gaps, and actually this view is very similar to the view of every religious scientist I know, and certainly the view I have. Now, there are other topics that come up in discussions of the universe and religion. One of the other ones is fine-tuning. So let me mention this one. Turns out that the fundamental constants of nature must be fine-tuned to allow life to exist. So one fundamental constant of nature many people know about is the speed of light. The speed of light is not infinite. It actually takes some time for light to get places. And it's a very well-known number, what that speed of light is. And there are a bunch of other constants that you have to specify to explain things that we've seen. It turns out that these numbers have to be very precisely tuned to get the world that we see. There are many, many examples. They do not really much depend on what life is. So basically, you can say, look, I want to have a universe that is more than 1 second old, because I don't think life can develop in 1 second. If you even just demand that, you will find fine-tuning problems. And they're really central problems in physics today. Many of us spend our whole careers trying to solve these fine-tuning problems. So one example is, I mentioned the dark energy in the universe, this thing that's 68% of the universe. If you want to have galaxies and life form, the energy density of dark matter must be fine-tuned to 1 part in 10 to the 120. So basically, the chance that this would happen by accident is equivalent to the chance if I ask you and you to go to different parts of the room and write down 120-digit numbers. Okay, just randomly write down 120 digits. And then we come back and we compare, and they're identical for the first 119 digits, and they're just off in the last one. Okay, that's what is happening in our universe. Okay? So that's what's fine-tuning. It seems like amazingly fine-tuned that these two numbers would be exactly that close together. Why is that? Okay, so let's go to the next slide. So there are a bunch of responses to this. This fine-tuning problem is well recognized, and there's been various studies about it. One is chance. You know, there's two numbers. They got to be something, so maybe just by chance it happened. You know this is not a good explanation, right? Because if this happened, if we actually did this experiment, this happened, not a single one of you would believe that there was chance. You would think that someone was texting the other person or something, right? So that's not a scientific explanation. Another idea which has been tossed around has to do with what's called multiverses. These are very poorly defined at the moment, and I can talk about that more if you want, but most of them are not really scientific ideas, not testable. A third one is that maybe there was a creator who built the universe with life in mind. That's certainly a possibility. And a fourth, which is not often discussed, but something that I favor, is that perhaps there's a beautiful and deep, yet to be discovered law of nature. Basically, maybe there's some reason that these two numbers were identical, which we don't understand yet, but maybe there is one in the future that we'll understand. For me, that then begs the question, where did that beautiful yet undiscovered law come from? And that basically leads back to 3, which is that there's a creator who is a far greater intelligence than us, who built the universe with that principle in mind and allowed life to go forward. I can give an example of 4 in real physics theories. Basically, you could ask the question, if you look at electrons all around the world, they all have the same charge, and they all have the same charge to an incredible degree of accuracy. And you might have thought that was a fine-tuning problem, and actually it was, until someone discovered a deep physical principle for why that is. And that physical principle is called field theory, which I won't get into here. But basically all electrons are just particle manifestations of something called the electron field. And that explains why they're all the same charge. And so this is not a puzzle anymore. This is not a fine-tuning problem anymore because we understand it. But we understand it with what is an absolutely beautiful concept called field theory, which I think points to a deeper intelligence in the universe. Okay, so I've gone through a number of things. Let me just give a couple closing thoughts. So we've come a long way in science, but if you have paid attention to what I've said, you know that we haven't got anywhere near the end. What is true for Newton, or what was true for Newton, is still true for us 300 years later. When we're asked, what did he do? He said, I seem to have been only like a boy playing on the seashore, whilst the great ocean of truth lay all undiscovered before me. And certainly that's the way I think we are now. People who think that we've reached the end, we've discovered everything there is to know, should look back and see many other people who have predicted that and been wrong for hundreds and hundreds of years. Following in the footsteps of Newton, Maxwell, Lemaitre, these are just people I've mentioned, many others in the history of science, we can find lasting meaning, great consonance and joy in a life of science coupled to a life of deep Christian faith. This perspective is beautifully expressed by an ancient poet who said, when I consider your heavens, the work of your fingers, the moon and the stars, which you have set in place, what is mankind that you are mindful of them, human beings that you care for them? And that's a perspective that's very, very old, but I think very, very current and relevant too. So in conclusion, science and faith, far from being in conflict, are actually, I think, best viewed as 2 expressions of the same human impulses, namely to think, to wonder, and to be awed by the world around us.